let's go on to derivatives. That limit of the slope of the secant line that we just talked about is called the first derivative. Okay, so where Desiree had suggested a graph of the slope of f of x that looks like this, that is just the graph of the derivative, right? So instead of slope of f of x, I could have called this the derivative, or more precisely, the first derivative of the function of x, also often referred to as f prime of x. Okay? Okay, so the derivative f prime of x of a function f of x is just the slope. The process of differentiation, what's that? That is the process of finding the limit of the slope of the secant line, or the process of finding the derivative, or the process of describing the slope of a nonlinear function. Okay? Of course, as you've already realized, the derivative or the slope of the nonlinear function is itself a function of x. It may be also a nonlinear function of x, such as this, or it may be a linear function of x, as Desiree initially suggested. Okay? Okay. Okay, so if you take a function f of x and you differentiate it, you'll get a different looking function called f prime of x, and that's a new function. If you put the value of x into this new function, then this new function will give you the slope of the original function, not the original function itself. Okay? Okay. Take a function f of x. If you differentiate it or find its derivative, you'll get a new function, which we call f prime of x. And if you take the value, a particular value of x that you had put into this function and you put it into the derivative, then this new function will give you the slope of the original function at that point, at the chosen point x, rather than the value of the original function. Okay? That's true by definition, but it's just something to keep in mind. Okay, and it'll become a little clearer once we see some examples. Okay, just some notation. There are lots of different ways of denoting the derivative, and they're all interchangeable, and you should just get used to seeing them in their myriad forms. Okay, and if you are, remember we're learning math driving around in the back of a pickup truck. So when you do that, it gets a little annoying to have lots of different names for the same thing. But it's a good way to apprehend reality. So just become fluent in the different names. Okay, so this is f prime of x, or f prime, or y prime. You'll see a common one is dy of dx, or dfx over dx. Yes?
And for your course, will you be using them interchangeably, or would you
I'll probably use them interchangeably. You'll see that the literature will use it interchangeably, so that's my excuse. There's sort of cultural antecedents to these things. So, F prime is the one that you most see with economists. Dy dx is more what you see with pure mathematicians. And these other ones you don't see that often, but you see a little bit. Okay? Okay. So that derivative, I just gave you all the different notation. Its interpretation is always as the slope. Okay? It's the slope of a function f of x. Now, in particular applications, you might interpret it as something slightly different. It's still the slope. You might think of it as the rate of change of f of x for some unit change in x. That really is the slope. Or in economic and financial applications, you might think of it as the marginal value of x. You'll see this term, marginal value of x. So if you've had no economics or finance before, this is a new term. And it always means the derivative of f of x. Okay? And therefore, it always means the rate of change of f of x for a unit change in x. Okay? Okay. So here's an example that you'll see in economics quite a lot. Cost functions. Suppose that instead of f of x, I have a function c of q. Q is now the independent variable. It takes the place of x. And c is the function. And it has this formulaic form. And it might look something like this. Q might be the quantity produced, and this is the total cost as a function of quantity produced. Actually, it probably won't look like this. In other words, I didn't check to see what q cubed minus 10q squared plus 40q looks like. And in fact, I can be sure that it doesn't look like that. It should go up. It should go up as q goes up. But you see, that's the power of calculus, because you can, once you have facility with calculus and you see a function, you don't have to graph it to see how it behaves under different circumstances. Okay? Okay, the marginal cost C prime Q is going to be the slope of this function. So just suppose that the function does look like this. What's interesting about this function is its derivative is going to look interesting, right? And I'll show you. So let's just draw what that derivative would look like. Okay. Desiree, do you want to help me, or does somebody else want to help me? Somewhere here, what would be the slope? So, okay, so here is the slope, first of all, is the slope positive or negative? Positive. Is it a big positive number or a small? It's a big positive number, right? So we're probably somewhere up here. Whoops. Hope I don't destroy this. Okay. You're frowning, so. Here, this, okay, so think of the tangent line at this point, right? Yeah, the tangent line goes up like that, right? And that's a steeply upward sloping line. So that has a very large positive slope. Okay? And so that's why I've got a plot somewhere here. For low values of Q, the slope is going to be very high. Okay? At this point, okay, this is why I got a pointer, so I don't have to stretch like that. At this point, what's the slope of the function? 0, right? So 0 is down here. So I know that it probably looks like this. But I don't know what's going to happen after this point, whether it'll go up, go down, right? So after the point 0, what's the slope here? Negative, right? So that means it's going straight through like that. Okay. Here, what's the slope? 0 again. So somewhere there, I've got to be coming back. Okay. And then here, the slope is positive, so it's going to be up here. And then here it's 0 again, so it's going to be like that. And then the slope is negative. Okay? I know that was a little quick if you have not met this kind of analysis before. So I'm going to do it one more time so you get a sense of it. This relationship between the function and its derivative is very central. Okay? And I don't care if you don't learn how to differentiate. But I do want you to understand, at least graphically, the relationship between a function and its derivative. Okay? Because that'll get you a long way. Getting that intuition behind it is really important. It's not important to understand the formulas. Okay? Okay, so let's do it for a simpler case. And let's go back to x and f of x. And suppose that I have the following function. Okay. Sorry, what's your name with the pink shirt? Kathy, right? Okay, so I'm going to ask you because you were frowning when this happened. This is my function, and I'll describe this in English, let's say. This is a function that starts out steep and upward sloping for values of x close to 0. Steep and upward sloping. And it stays very steep, but it gets less and less steep as x increases until, let's say, it gets to the value of 5 at where x is equal to 5. It's not steep at all, it's not upward sloping at all, it's flat. And after that, it's downward sloping. So for values of x between 0 and 5, it's upward sloping. For values of x above 5, it's downward sloping. Okay? Okay, so let's put that up. And I want you, Kathy, to tell me what the slope would look like. Sorry, that has to get up there a little bit higher. Okay. Okay, so Kathy, for values of x less than 5, we know that the function is upward sloping. Will this, if I had to plot the slope here for values of x less than 5, will the number be a positive number or a negative number? Or 0? Positive, right? And if it's close to 0, is it going to be a big positive number or a small positive number? In other words, so by positive, you mean that it's upward sloping. Is it very upward sloping here, or is it only a little bit upward sloping? Is it gradually upward sloping? It'll be a big positive number, right? So it's going to be up here. Now, at the value x equals 5, what's the slope going to be? 0. So that's probably a point on this function, the f prime of x. For values greater than 5, we said that the function is downward sloping, and it gets more steep as x increases. So downward sloping means it has a negative slope. So it's probably something like that. And looking at this, it's probably a straight line. So the function that describes the slope of the function above, i.e. its derivative, here is a straight line. Okay? If you plug the value 5 into f of x, you'll get some number, whatever that number happens to be. If you plug the value 5 into its derivative, you'll get the slope of the original function. Everybody see that? This is what I need you to internalize. Okay? It doesn't have to be in the next 2 minutes, but in the course of the next year or so. Yes? Oh, yeah. By definition, when it's going down, it has a negative slope.
So anytime you go over that, over your reach, you're going to go below.
That's right. So at that point, it has a slope of 0 because you're flat. So generally, if you start up in the positive territory, if you start out with positive slope, and then you hit a point where you're flat, for most functions that you'll see, beyond that, you'll have a negative slope. For it not to have a negative slope there, it would have to be an unusual function. For example, if this was a plateau, then this slope would go like that and then would hang out at the x-axis for a while. Okay, yes? Yeah. Yes. So that goes back to this bullet point. The derivative depends upon x in some way. That is, the derivative is also a function of x. Okay? When x is substituted into the derivative, the result is the slope of the original function. Okay? So what I'm saying here is this is the original function, f of x. If I plug in 5 into that function, I get some value. I didn't tell you what that is, but let's say that's 20. I then work out the derivative of this function, either by differentiating or by some graphical method of determining slopes, and I find that the derivative of that function, which I call f prime of x, looks like that. If I plug 5 into f prime of x, then I get a number here, 0. 0 is the slope of the original function. Okay? Yes?
The derivatives will always be a straight line?
No. No. This was a simple case where actually I started out with a quadratic function, and so they happen to have derivatives that are straight lines, and you'll see why in a second. But look here. Here I had a more complicated function, and its derivative looked less complicated than the function itself, but nevertheless fairly complicated. In general, it's usually the case that the derivative will look a little simpler, closer to linearity than the function itself. Remember, the interpretation of the derivative is the rate of change, or how the function changes for a unit change in the input variable. So very commonly, the instantaneous speed, if you're driving from here to DC, every instant you have a different speed. You know, there aren't any cars in front of you, you're driving at 70 miles an hour, or maybe more. And then you hear a police car, you're going to drive at 40. Okay, so that is, so at different instants, you have different speed. Think of that in the same vein as a nonlinear function. At different points, different values of x, you have different slopes. Okay? When you're going very fast, you're getting towards DC very quickly. When your slope is very steep, you're covering a lot of distance in this axis very quickly. Okay? So in general, in any kind, I mean, that's just a speed example, but in any kind of social analysis or scientific analysis, you'll have phenomena that are related to other phenomena. That's the functional relationship we talked about in the last session. And then you'll want to know whether that functional relationship is, what's the rate of change of that functional relationship? If you change x a little bit, will you have a huge change in y, or only a little change in y? Okay. As an example here, if this is a cost function, if I'm at this point and I increase my output, because the slope here is very gradual, my total cost won't rise too much. But if I'm here and I increase my output a little bit, my total cost will rise a lot. And there's probably an underlying technological reason for the shape of this cost function. For example, it could be that here you are surpassing the limits of capacity. You know, if you think about a classroom, if I add an extra student into this class, there's going to be no change in the quality of everybody's experience. But if this were full and I added an extra student, then I might have to expand to another classroom. And so my cost, let's say, would increase substantially. Okay? Yes? No, you could do that for every function. In fact, so if you didn't know calculus at all, and you simply sat there working out tangents, and then plotting the slope that you derive from that tangent and associating it with each value of x, you would be able to construct the derivative function. Okay? Calculus is simply a method of constructing the formula for that function without having to do the graphical analysis. Okay? Okay. So that's the interpretation of the derivative. Everybody okay so far? Okay. Now, of course, and this is a common trick that people do in math. Once you understand something and you think you've grasped it, then they ask you to iterate the logic. That is, repeat the logic on itself.